Okay, so we proved the following theorem of Friedrichs. So u in W1p of omega, then there exists un in d of Rn such that un goes to u in Lp of omega, and for all 1 less than equal to I less than equal to n, du by dxi, dun by dxi goes to du by dxi in Lp of omega prime for all omega prime relatively compact subsets of omega. So this was the theorem which we proved. So let us now look at some applications of this. So the first theorem, this is called the chain rule, the function of a function rule in calculus, which we have here. So let 1 less than equal to p less than or equal to infinity, omega in Rn open set, and g from R to R C1 function, that means continuously differentiable, and such that g of 0 equal to 0. Assume further mod g prime is less than or equal to m. So it has a bounded derivative. Then if u belongs to W1p of omega, we have g composed with u belongs to W1p omega as well, and d by dxi of g composed with u is the usual thing. So you first differentiate with respect to whatever you have, and then differentiate the inside. So you have g dashed composed with u, and then du by dx. Okay, for all 1 less than equal to I less than equal to n. Okay, so what is g composed with u at any x? This is g of u of x. So you see, this is the function of the function rule or the chain rule. You have, if you want to differentiate this in normal calculus, you would have done g dash ux into du by dxi, and that's exactly we are having the formula which we have in mind here. Okay, so proof. So let so g0 is 0 implies, by the mean value theorem, you have that mod gs is less than equal to m times mod s. Okay, so that is the for all s in R. So this is just an application of the mean value theorem, which says that gs minus g of 0 is less than equal to m times mod s minus 0, where m is the maximum of the derivatives. Okay, so this implies that g composed with u belongs to Lp of omega automatically, because mod g of u of x is less than m times mod u of x, and therefore if u is in Lp, g is also, g composed with u is also in Lp. Also g dash u du by dxi, again g dash u is composed with u is bounded by m, and mod du by dxi is in Lp, so this also belongs to Lp of omega. So it enough to prove star. Once we have this formula for the derivative, it automatically implies that g composed with u is in Lp, and its first derivatives are all in Lp, and therefore it is in W1p, and that is exactly what we want, in addition to the formula which we have. So let us do it in two cases. So case 1, where we have 1 less than equal to p strictly less than infinity. So let un belong to d of Rn, un goes to u in Lp omega, and dun by dxi goes to du by dxi in LP omega prime for all omega prime contained in omega. So, we are applying Friedrich's theorem. Okay. So, then G of un converges to G of u in LP of omega. Why? Because mod G of un x minus G of u of x is less than or equal to m times mod un minus unx minus u of x. And so, if you integrate both sides, the power p, you will get that this goes to 0. So, this also has to go to 0. Also, for a subsequence, you have that g dash of unx will converge to g dash of u of x, because we have for a subsequence unx will go to ux pointwise almost everywhere, and therefore g dash is a C1 function, and therefore the g is a C1 function, so g dash is continuous, and therefore this also goes to 0. Now we will henceforth work with the subsequence, so I am not putting the subsequence notation here unk, I am going to work with that subsequence, so I will call it un itself. Okay. Now let phi belong to d of omega. So, let omega dash be relatively compact in omega such that support of phi is contained in omega dash. Okay. So, you have omega and you have a compact set k here, which is the support of phi. I can always find by the properties of the topology in Rn that another omega dash which contains omega, this support. Okay. So, now you have that integral on omega g composed with un d phi by dxi dx, which is equal to integral on omega dash, because I can it's a support of phi. So, g composed with un d phi by dxi dx, and now everything by the standard un is a smooth function, g is a smooth function, so this is a smooth function, this is also a smooth function. So, by Green's theorem, which is integration by parts, you get that this is equal to minus integral, the traditional one. So, g dash composed with un dun by dxi into phi dx over omega. There is no boundary term because phi vanishes on the boundary, since it is a C infinity function with compact support, therefore it vanishes on the boundary. So, there is no boundary term on omega prime. Okay. So, now we are going to pass to the limit. G composed with un goes to u in LP. Phi is a fixed C infinity function with compact support. So, we have seen this many times already. So, this will converge to G composed with u d phi by dxi, and this one will converge. So, minus integral g dash un goes pointwise to g dash u, dun by dxi goes in LP, and phi is a fixed function, C infinity function with compact support, and therefore by again you can apply whatever favorite theorem you like, the dominated convergence theorem or any other theorem. So, you have, if you have for instance a sequence which is uniformly bounded in L infinity converging pointwise, and a function which is converging in L infinity LP, then the product will converge in LP. Okay. So, this and consequently you are multiplying it by phi, and therefore this will go to integral over omega dash g dash u du by dxi times phi dx, and then we can replace now omega dash by omega. So, this is equal to minus integral omega g dash u du by dxi phi dx, and that is exactly what we wanted to prove, and so prove star. So case 2, this is easier, p equals infinity. Okay. So if again phi is in d of omega and support of phi is contained in phi dash, which is relatively compact in omega as before, and then if u is in w1 infinity of omega, then what do you have? In fact this implies u belongs to w1q of omega prime for all 1 less than or equal to q less than infinity, equal to infinity also, but I do not want that now. And now we are in the previous case and case 1 applies and the result follows. So we have the chain rule. So now the remark, important remark, g of 0 used to show equal to 0 used to show that mod gx is less than or equal to m times mod gs, implies g of u, g composed with u is in LP. Okay, this was the only place where we needed the fact that g of 0 is 0. Suppose omega is bounded, then by the mean value theorem you have g of s minus g of 0 is less than or equal to m times mod s, and that implies that g of u of x, so g composed with u of x mod is less than or equal to mod g of 0 plus m times mod u of x, and omega bounded means finite measure, implies mod g of 0 constant function is in LP, and therefore you do not need and therefore this implies that g composed with u is also in LP. Okay. So if you are in a bounded domain, then you can still use this the chain rule without the hypothesis g of 0 equal to 0, which we are now going to do. Okay. So we are going to prove another interesting theorem, very nice theorem. So let omega in Rn bounded open set. One less than or equal to p less than infinity, u is in w1p of omega, implies mod u is also in w1p of omega. Okay, and d mod u by dxi equal to sin u du by dxi, 1 less than to I less than to n, where sin u of x will be plus 1 if ux is positive, 0 if ux is 0, and minus 1 if ux is negative. Okay, so we will prove this result now. So let epsilon be positive, small positive number, okay, and define f epsilon of x or t equals square root of t square plus epsilon. Okay, so then f epsilon belongs to C1 of R, and f epsilon dash of t is nothing but t by root of t square plus epsilon, and this shows that mod f epsilon is less than or equal to 1. F epsilon 0 is not 0, of course. However, omega bounded implies that chain rule applies. And therefore, you have that u in W1p of omega implies that f epsilon of u is equal to f epsilon composed with u belongs to W1p omega, and d by dxi of f epsilon composed with u is equal to u by root of u square plus epsilon of du by dx, 1 less than equal to I less than equal to n. Okay. So now mod f epsilon t by minus t is less than equal to root epsilon. That is a very trivial inequality for you to check. So check. Just comes from the fact that t square plus epsilon is less than equal to t plus root epsilon whole square. That is all. It just comes from that. So t square plus epsilon is less than or equal to t plus root epsilon whole square. Okay, so it's just a consequence of this fact, and therefore you have that f epsilon composed with u converges to mod u in LP omega. Now u by root of u square plus epsilon du by dxi converges to u by root of u square plus epsilon converges to sin u, because if u is positive this will go to u of x plus 1, if u is negative this will go to minus 1, if u is 0 it is 0 anyway. So, so this goes to sin u du by dxi pointwise. Further, you have that mod u by root of u square plus epsilon du by dxi minus sin u du by dxi power p. Both of them in modulus are less than equal to mod u du by dxi. So, this will be equal to 2 power p mod du by dxi power p, which is integrable because u is in du by dxi is in LP. Therefore, by the dominated convergence theorem implies that d by dxi of f epsilon composed with u goes to sin u du by dxi in LP of omega. So, this means that f epsilon of u goes to u mod u in W1p omega implies mod u belongs to W1p omega. Okay, and of course the derivative is what we have, okay, because it converges, so therefore the derivative and du by dxi equal to sin u du by dx. Okay, so that proves this. So it has very nice applications which we will see later on. Okay, so theorem again, consequence of this theorem. So omega in Rn bounded open set one less than equal to p less than infinity u in W1p of omega. Then for any t in R and any 1 less than equal to I less than equal to n, we have that du by dxi equal to 0 almost everywhere on the set for x in omega ux equal to t. So proof. So let us take u greater or equal to 0. So that this implies that u equals mod u. Okay. So sin u du by dxi equals d mod u by dxi, which is equal to du by dxi. So this implies that on the set u equal to 0, we have du by dxi equal to 0. When I say this is equal to this, these are of course LP functions, so they are all equal almost everywhere. So this means that this du by, because du by dxi is sin u du by dxi, and sin u is 0 on the set u equal to 0. So this is du by dxi equal to 0 almost everywhere. Okay. Now if u is in W1p of omega, we write u equals u plus minus u minus. Okay, so u plus of x is 1/2 of mod ux plus ux, which is the maximum of ux and 0, and u minus of x is 1/2 of mod ux minus ux, which is equal to minus minimum of ux and 0. So both are non-negative functions, and you can write it, and then of course you will have mod u is equal to u plus plus u minus. This is something which you would have seen many times when doing a real analysis, and therefore if you have set of all x in omega such that ux equal to 0 is the set of all x in omega such that u plus x equal to 0 intersection set of all x in omega such that u minus x equal to 0, and du by dxi equals du plus by dxi minus du minus by dxi, and therefore this implies that du by dxi equal to 0 almost everywhere on this set. So for any t in R, consider the function u minus t. So then apply the theorem for 0, and then you get this. Okay, so this is a thing which says that if you have a level set, namely ux equal to t, then the derivative of u, distribution derivative, will vanish almost everywhere on that set. Of course, remark, the set x in omega ux equal to t may itself be of measure 0, because very often you have smooth functions, they will unless the function is flat, given any value, the set where it takes this value will be a set of measure 0, in which case above theorem gives no new information, because you are saying something is 0 almost everywhere. Well, it may not even be 0 at all, because the set itself is of measure 0. Okay, but however, if you have a function which is like this, so in portions like this where the constant value is attained, so there you will have that u dash will be 0 almost everywhere, just like in the calculus case. Okay, so this is what we have. Okay, now we will state a theorem. I won't prove it. The proof you can read in the book which I suggested to you, Topics in Functional Analysis and Applications. But the proof is almost similar to the chain rule proof we have, a little more, you have to be a little careful here and there, but otherwise there are no new ideas, so we will save some time. So we will just state it. So this is called Stampacchia's theorem. let omega in Rn be a bounded open set. Let and 1 less than or equal to p less than infinity, and f from R to R Lipschitz continuous such that, so Lipschitz continuous function is of bounded variation, absolutely continuous, etc., and therefore you have that it is differentiable almost everywhere, okay, and the derivative is bounded by the Lipschitz constant, okay. So f dash is continuous except at a finite number of points. T1 to Tk. If u belongs to W1p of omega, then f composed with u belongs to W1p omega, and d by dxi of f composed with u is whatever you are going to expect, which is equal to at any x equal to vi, which is given by the following definition. This is f dash u du by dxi at any x if ux does not assume one of the prohibited values, so t1 to tk, and 0 if ux belongs to t1 to tk. This we have already seen this in the, suppose a typical example for us is the function mod ft equals mod t, and there we saw in fact this is precisely sin u is precisely given by this expression, okay. So this is a generalization of the previous theorem, and as I said it does not produce any new ideas in the proof, it is only technically a little more complicated, and therefore we will omit a proof, and then we will continue with some other properties based on the chain rule later.